All right, ready? Okay, thank you very much. This will be the last Hyperwall of the day, thankfully. And I think we have one more tomorrow, right? Yeah, but I won't be there for that. One of the key questions about climate change is how it's going to impact things that we feel, right? We don't live in the global mean temperature. We don't feel the effects of the global mean sea level rise. All of these things, the amount of heat that's going into the ocean, these are esoteric things that scientists use to keep track of what's going on, but they're not what affects people. What affects people is the weather, and it's the events, and it's the extremes. And we have been working, and particularly Amber here is going to explain how those extremes, how the weather is being impacted by the climate, how wildfire is being impacted, and how they in turn affect the climate itself. And so thank you very much, and we'll be happy to take questions afterwards if you have any. Thank you.
Hello, my name is Amber Soya, and my chair is at NASA Langley Research Center in Hampton, Virginia. My expertise is in fire, and my interest is in looking at fire and aerosols, how they interact on the biosphere or our landscapes, how they interact in the atmosphere, and also how they interact with climate systems. So with that, let's get started. Next slide, please. So if you look at the panel in the middle on the far right, the cartoon, you'll see some feedbacks to climate change. We know that fire and smoke changes albedo, or the relative reflectance of the landscape and the atmosphere. So this is a feedback to the radiation balance. We also know that aerosols tend to inhibit precipitation in the near field. There's a lot of processes between aerosols, smoke aerosols, and clouds and precipitation that we just don't understand. But we do know that smoke is a deadly pollutant. It's a pollutant that has been statistically found to increase hospital visits, to increase respiratory illnesses, heart attacks, and even death. So it's a dangerous pollutant. So if you think that you've heard about a lot of fires in the news lately, you are not wrong. You have, and these have not been sensationalized. In fact, in 2021, four of California's largest fires burned. In 2020, 5 of California's largest fires burned. That's a lot of fires in the last couple decades. In 2018, the most expensive disaster globally was the Camp Fire. That's according to Munich Re. Every year there's new records set, and then they're being broken. In 2017, the Thomas Fire burned in California and set the worst fire record. And in 2017, a fire burned in British Columbia in Canada that broke the record, the worst fire. And in 2018, both of these records were broken. And also we see increasing fires and largest, worst, deadliest fires: Colorado, Kansas, Oklahoma, New Mexico, Georgia, the Sierra Nevadas, Texas, just all over. And next slide, please. It's not only in the United States and North America, it's all over the world. So we see the Mediterranean also increasing, and there's been many deadly and worst fires across the Mediterranean, and even in Sweden, where you don't typically hear about bad fires. Russia's had a number of bad fire seasons, catastrophic fires. In 2010, Russia had a fire that burned for several months in peat. And this fire was estimated to result in the deaths of 56,000 people due to the smoke, smog, and heat of this particular event. And that is also according to Munich Re. In South America, 2017 was Chile's worst fire year. 2019 and 2020 were both bad in Brazil, bad burning year that endangered endangered flora and fauna. Also in 2020, Brazil, Argentina, and Venezuela had worst fire years. So that was regional. That wasn't just one country. That was a whole group of countries. Australia has had its worst and deadliest fires in the last 2 decades. The Black Summer Fire that burned in 2019 and 2020 and circumnavigated the stratosphere. Even now, the smoke did. And 2019, the Black Saturday fire. And you know that things are awry when we have the worst fires burning in Greenland, of all places. Next slide, please. So you might wonder, what does NASA have to do with fires, and why are we? What do we have to bring to the table when it looks to fire? When it comes to fires, we have a host of satellites that are viewing the Earth during the day and during the night. And it's not just viewing, it's data. It's data on precipitation and clouds and albedo change, healthy vegetation, drought-affected vegetation, and yes, indeed, fires. So we take these data products and we share them with the world. And we also work with other space agencies like ESA and JAXA and any space agency that is willing to work with us. So we put these data together, and give me a couple seconds after this next slide before you start the movie. And the reason for that is this movie is going to be active fire detections from VIIRS, and it's going to run from January to September. And in this slide, in this movie, I'd like for you to look at the bottom right where Australia will be burning, because it's the southern hemisphere summer. So it will burn in Australia first, and then I'd like for your eyes to move up to the southeast United States by February, March, April timeframe. Okay, let's get this movie started. So as you can see, there's fires burning in the southern hemisphere in Australia. And then if you move your eyes up to the southeast United States, you see agriculture burning, which is bigger than you thought, right? And also prescribed fires. And across the whole temperate zone, you'll see the same. The whole area is lit up. And then as the northern hemisphere warms and the fire season begins, you see fires burning in the boreal and Arctic in Siberia, Alaska, and Canada. And you'll also note that fires are burning in Africa all the time, in the northern and southern hemisphere. Fires are, Africa is truly the fire continent. Fires are also burning in the tropics in South America, so these are also evident. And so what do we do with all these data? Well, we can put together lots of statistics, and we know when things are changing, and we can tell stories. Next slide, please. In this movie, what you're seeing is the green smoke is from fires. It's organic and black carbon. The red and yellow are active hot fire detections. The red smoke, the red is actually dust. Blue is sea salt. White is sulfates. So you can see the green, organic and black carbon streaming from Africa right now as the globe is turning. And you see the red dust from the deserts. And now we're moving over and we see Indonesia on fire. So you see the green smoke coming from Indonesia, the black and organic carbon. Also the dust from the desert, sea salt, storms, and we're going to move into the southern hemisphere winter, summer, southern hemisphere summer, where we see fires burning and we see the green organic carbon, black carbon that's emitted from these fires. And the smoke is going down and mixing with the sea salt near Antarctica. And the reason this is significant is because aerosols on ice will cause it to melt more quickly on snow and ice. So we see again the smoke mixing with the sea salt. And then as we come up on Patagonia, we see dust coming off of that desert. So we have smoke and dust aerosols mixing with the sea salt in Antarctica, which could be an effect, a feedback to climate. And as we move along, we're going to take a look at Africa again. When we move to Africa, we're going to see the organic carbon and the green carbon, and the green, black and organic carbon moving from the east to the west. And we also see the dust moving from the west to the east in the northern hemisphere. And what this video shows you is how connected we are as an Earth. So now you see the green, organic and black carbon traveling to South America. And the rainforests are there because of the nutrients that are provided by the smoke and dust in geologic time. So pretty neat. We are really definitely one Earth. Next slide, please. So fire is a natural process. Every ecosystem exists with a particular fire return interval, a surface fire or a crown fire. So we've got a balance. We've got a balance between good fire when fire weather is low that we can control, or allow fuels to build up and we have high fire weather, and then that would result in fire that we couldn't control or a bad catastrophic fire. Fires by themselves have a lot of good qualities. They can burn and control the fuels, so they minimize fuels. They can open seed cones. There's a lot of species that rely on fire to exist. They decrease invasive species and promote the species that we want, native species or endangered flora and fauna. So fires are not all bad. This isn't a one story. Next slide, please. So now we're looking at the boreal and the Arctic. In the top right, I'm showing a buildup index. And what this means is it's a fire weather variable that's significant of how much fuel is dry enough, deep enough to burn. So the big fires. And if you notice in the white to the right of the right is increases, yellows and oranges and reds. So the whole circumboreal, the whole circumarctic are increasing over the last 42 years in the buildup index. Just to the left of that in the top panel, we have temperature increases, and also temperature is increasing in the boreal and Arctic zones, looking at this polar view. The next panel, we see Northern Eurasia, and the one below that, the graph is North America. The solid line is temperature, and the broken line is buildup indices. These are all increasing in Northern Eurasia and North America, but particularly in Northern Eurasia. Next slide, please. So the reason we care about this is because the type of burning, and this is where the carbon is stored. The Republic of Sakha this year in 2021 had its largest year in the satellite record, which is over doubled the mean of any previous years. 2020 was the previous worst year, and now 2021 in the Republic of Sakha. This is a huge area. It is almost twice the size of Alaska, our biggest state, which is bigger than many countries, territories, and states. And this particular region is permafrost lane, and it stores carbon. And what I mean by that is because it's cold, decomposers can't decompose all year. So the partially decomposed leaves and twigs pile on top of each other year after year for hundreds of years, for millennia. So one fire has the potential to burn down deeply and release carbon that's been stored for tens to hundreds to even thousands of years. Forget forever or in geologic time, altering the landscape for a long time. Next slide, please. Now we're going to look at the Arctic system, because this is where the warming is happening first. This is where it's predicted to occur, and indeed it is burning. If you look at the middle panel on the far left, you'll see that 2020 was the worst fire season, the earliest and the largest in the Arctic. And before that it was 2019. So the earliest and largest fire seasons just occurred. 2019 was twice as large as the next large season, 2013. And 2020 surpassed 2019 by 25%. And if you look at the top right, that's the SAGE instrument. And SAGE looks at aerosols in the stratosphere. So we live here in the troposphere, and above that is the stratosphere. So that means that these aerosols from these particular fires, from the Australian fires, and also from volcanoes, got into the stratosphere where we can detect them, which is another very cool instrument, the way we look at the Earth. Next slide, please. You may wonder why this is important. Why do we care? Well, we care because we are one global system. You know that sea ice is decreasing, temperatures are increasing, the smoke and the aerosols are landing on snow and ice, causing them to melt more quickly. And the other feedback is that as the permafrost thaws, There's more melt to the Arctic, which can influence the thermohaline circulation. So that's another feedback to the climate system. We have the warming that feeds the fires, and the fires that then in turn feed the warming on the snow and ice. That's why we have to care, is because we are all one planet. Next slide, please. I'd like to end with saying that climate-induced fire regime and ecosystem change is here and now on our landscapes, and it has been in the Boreal and Arctic for the last couple decades. NASA has the science and data to be able to address some of our science questions, to really dig in and figure out these processes. So our Earth observing systems are able to work now in order to tease apart our Earth's problems, issues with climate change. Biomass burning is neither good nor bad. It should be seen as a tool on our landscape, and also as a fundamental process, one that we need to learn to live with. So I'd like to end with a personal note from a friend and colleague. He sent this note after we sent condolences for the Attica fire that burned in Greece in 2018. He started with, the tragedy is really too much to comprehend in one gulp. Then he went on to talk about the mass media and how much attention the fire was getting and wondering why this fire happened. And he ended with, if only they had devoted 1/100th of the time and effort every year for prevention. So he's saying the same thing. We need to deal with fire up front before these catastrophic events. We need to learn to live with fire again on our landscapes as climate changes all around us. Thank you so much for your time. Greatly appreciated. Bye-bye.
So if anybody has any questions related to the work that we do on this, I'd be happy to answer them if we can. Thank you.
Thank you. Can you hear me okay? So about a month ago, a friend of mine sent me an article that said that that 100 years ago, basically, the total amount of acres burned globally was about the same as today. And I wanted to ask if I couldn't actually find a reference to somewhere else where I looked, and I'm wondering if that's actually an accurate claim.
Yes, it is, and the reason why. So I don't know the exact time period that was referred to, but the reason why that is likely to be true is because burned area is not the same as wildfire. So burned area includes all of the agricultural burning that occurs, and we have been. As a global society, we have been reducing the amount of agricultural burns over time. So we're doing less of that than we used to because of the obvious consequences of that. And so while we're seeing climate impacts on wildfire, right? So that's happening in unmanaged lands. The total amount of burnt area is a very different metric. And so that's been going down. So it's possible that was higher 100 years ago. What we're seeing now, and you have to be careful because there's a lot of anthropogenic impacts on fire, as we were discussing, right? You know, forest management, incursions and human ignition play a large role in what gets burnt. And so, looking for a climate signal in fire, you need to look carefully at the data, and you need to take out the agricultural stuff, take out the human ignition stuff, take out the places where forest management has played a role, and then look at the places that are left. And that becomes that's a harder job, but I think we're now quite confident that both the drying from the increased evaporation, because there's more evaporative draw now, the heat itself, and the encroachment further north of lightning. So lightning is now moving poleward as thunderstorms move poleward, and so places like Alaska and the boreal regions are seeing a lot more lightning strikes. And in dry areas where it's been hot, that's causing more fires.
So the administration and Congress just invested an unprecedented amount of resources into forest resilience and wildfire resilience through the infrastructure bill. How is that affecting NASA? What hopes do you have for how our agencies address wildfire resilience moving forward?
So we're involved in a number of interagency partnerships, both with FEMA and with NOAA and with EPA, related to like short-term reactions to fire. So we have this project FIRMS, the Fire Information Resource Management System, I think. Anyway, it's firms.nasa.gov, where we kind of pull together all of the real-time data on what fires are being seen, what smoke is being seen from satellites, so that we can feed that directly into emergency responders efforts. We are working hard on improving our ability to kind of look historically. We have a new kind of pilot project where we're pulling all of that data, putting it into the cloud, and allowing that to be kind of placed on top of other important data sets like infrastructure, houses, populations. And so we're trying very hard to do that. And then we're trying to integrate that with the forecasts, both on the short term for what the fire weather will look like in a couple of days' time, but also in the long term. So our climate models now are trying to predict the extent of fire that you would get under different climates, or what you would have had in undisturbed climates. And we're working with all of the agencies where we can to do that. As more resources come in, what we would hope to do is to really fund those kind of interagency teams so that they can pull together that data more efficiently and more usefully, working with the people who need it directly. Okay, well, thank you very much for coming, and thank you very much for attending all of these Hyperwalls that we've had. They're all online, and so if you missed any and you want to go back, then just go to the US Center's YouTube page, and you'll be able to find all of the events that occurred here available for streaming at your leisure. So thank you very much, and have a good trip home, folks.